What if everything you see around you, the stars, the air you breathe, even your own body, is just the tip of an invisible iceberg? Beneath the surface of reality lies a hidden ocean of energy, where particles flicker in and out of existence, and the very fabric of space hums with secrets. This isn't science fiction. It's the world of quantum fields, the invisible forces that shape our universe in ways so strange they defy common sense. Think about the famous double-slit experiment, where particles act like waves until you look at them. Then they suddenly choose to behave differently. That's just a tiny glimpse into the quantum weirdness we're diving into today. These fields aren't just background noise. They're the architects of reality itself, governing everything from the mass of atoms to the fate of the cosmos. And here's the wild part: we've only scratched the surface. Over the next few minutes, we'll unravel 30 mind-bending theories about these quantum fields ideas that could rewrite our understanding of existence. Some will sound like magic, others might keep you up at night, but all of them will make you question what's really out there, ready to peel back the curtain. Let's jump in. Now let's dive into our first theory, one that flips the idea of nothingness on its head. Imagine the emptiest space you can think of, a perfect vacuum where not a single particle exists. You'd assume it's just empty, right? Wrong. Even there, quantum fields are buzzing with activity. This is the zero-point field, a sea of energy that never quiets down, no matter how cold or empty the universe gets. It's like static on an old TV screen, always there, even when nothing's broadcasting. This zero-point energy isn't just a curiosity. It might hold the key to one of cosmology's biggest mysteries, dark energy. See, when scientists calculated how much energy this quantum static should contribute to the universe, the numbers were catastrophically wrong, off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. This mismatch is called the cosmological constant problem, and it's a glaring sign that we're missing something huge about how quantum fields and gravity interact. Now, here's where things get even wilder. Could we tap into this endless energy? Sci-fi loves the idea, but reality is harsh. The zero-point field is everywhere, but it's also smooth. You can't grab a piece of it because there's no difference between one point and another. It's like trying to collect water from a perfectly flat ocean. Some theories suggest exotic materials or quantum tricks might one day extract a tiny fraction. But for now, this energy remains locked away, teasing us with its untapped potential. So the next time you stare into the night sky, remember, even in the void between stars, the universe is never truly at rest. The zero-point field hums silently, a reminder that reality is far stranger and more alive than it seems. Now, let's rewind the cosmic clock to the very beginning, a fraction of a second after the Big Bang. Picture the universe not as the vast expanse we see today, but as a seething, ultra-dense soup of energy where quantum fields were anything but calm. Even in that primordial chaos, tiny ripples, quantum fluctuations, were already at work. These weren't just random blips, they were the seeds of everything. Here's how it happened. During cosmic inflation, the universe expanded faster than light itself, stretching those tiny quantum ripples across the cosmos. Think of it like blowing up a balloon with microscopic wrinkles. As the balloon inflates, those wrinkles grow into mountains and valleys. In the same way, those stretched-out quantum fluctuations became the blueprint for galaxies, stars, and even the cosmic web we see today. Without them, the universe might have been eerily smooth, with no structure at all. But inflation doesn't just explain why the universe is lumpy, it also opens the door to the multiverse. If inflation can happen once, why not over and over in countless pockets of spacetime? Some theories suggest that each bubble universe could have its own unique physics, born from different quantum fluctuations. Our universe, with its perfect balance for life, might just be one lucky roll of the cosmic dice. So the next time you look up at the night sky, remember, the galaxies above you might owe their existence to quantum jitters smaller than an atom, amplified by inflation into the grand tapestry of the cosmos. And if the multiverse is real, there could be endless other skies out there, each with its own story written by the same quantum rules. Now, let's shift our focus to something a little closer to home, or at least to the particles that make up everything around us. Imagine the universe as a vast, invisible ocean, and every particle swimming through it is slowed down by a kind of cosmic molasses. That's the Higgs field in action. Unlike other fields which might push or pull particles, the Higgs field does something far stranger. It gives them mass. Here's how it works. As particles move through the Higgs field, they interact with it, and that interaction is what we perceive as mass. Think of it like wading through water. The more resistance you feel, the more mass you have. A photon, which zips through the Higgs field untouched, stays massless, while a top quark, which interacts strongly, ends up being one of the heaviest particles we know. This isn't just a neat trick of nature, it's the reason atoms, planets, and even you exist. Without mass, everything would fly apart at the speed of light. The discovery of the Higgs boson in 2012 was a monumental moment in physics. It confirmed a 50-year-old prediction and filled in the last missing piece of the Standard Model. But here's the twist. The Higgs field might not be the whole story. Some theories suggest there could be deeper layers, like multiple Higgs fields or even entirely different mechanisms for generating mass. For example, in supersymmetry, every known particle has a heavier superpartner, and some of those could play a role in mass creation too. So while the Higgs field explains so much about our universe, it might just be the tip of the iceberg. What if there's a hidden ocean of fields beneath it, each with its own rules? The search for answers is far from over, and every new discovery could rewrite our understanding of why things have weight and what that really means for the fabric of reality. Now, let's dive into one of the most unsettling possibilities in quantum physics, something that could rewrite the universe as we know it in an instant. Picture our universe's vacuum not as empty space, but as a fragile, high-energy state like a ball perched at the top of a hill. It's stable for now, but one tiny nudge could send it rolling into a lower energy state, a true vacuum. And if that happens, the consequences would be catastrophic. Here's how it could unfold. A random quantum fluctuation somewhere in space might create a tiny bubble of this true vacuum. Inside that bubble, the laws of physics as we know them would change. Particles might get different masses, forces could behave unpredictably, and even the structure of atoms could unravel. The worst part, this bubble would expand at the speed of light, swallowing everything in its path. One moment, the universe is normal, the next, it's gone, replaced by something entirely alien. But before you panic, let's talk plausibility. The idea comes from solid math in quantum field theory, and our current measurements suggest the Higgs field might indeed be in a metastable state. That said, the odds of this happening in any given year are astronomically low, like winning the lottery trillions of times in a row. Plus, some theories suggest that even if a bubble formed, it might not destroy everything. Quantum effects or unknown physics could stabilize it. So while vacuum decay is a fascinating and terrifying thought experiment, it's likely not something we'll ever face. Still, it reminds us just how delicate the balance of our universe really is, and how much we still have to learn about the quantum fields that shape reality. Now, let's shift gears to something equally mind-bending but far less apocalyptic: quantum entanglement, but with a twist. We're used to hearing about particles being entangled, like two electrons mysteriously linked no matter how far apart they are. But what if I told you entire quantum fields, the very fabric of reality, can be entangled too? Imagine two patches of space light years apart, where the fluctuations in their quantum fields are perfectly synchronized. Change one and the other instantly responds, defying our usual notions of distance and locality. this isn't just theoretical. In quantum field theory, entanglement isn't limited to particles. It's a property of the fields themselves, weaving the universe together in ways we're only starting to grasp. Here's where it gets wild. Some physicists like Juan Maldacena and Leonard Susskind have proposed a radical idea called ER=EPR. It suggests that entangled quantum fields might be connected by microscopic wormholes, tiny bridges in spacetime. In other words, entanglement could literally be bending the fabric of the universe, hinting that spacetime itself emerges from these tangled fields. So, does that mean the universe is one giant web of entangled fields, with spacetime stitching it all together? Maybe it's a bold idea, but it's backed by serious math. And if it's true, it could rewrite our understanding of reality, showing that the connections between things, no matter how far apart, are far deeper than we ever imagined. What do you think? Could entanglement be the hidden glue of the cosmos? Let's keep exploring, because next up, we're diving into another puzzle: axion fields and their potential role in solving the mystery of dark matter. Now, let's turn our attention to one of the most elusive mysteries in the cosmos: dark matter. Scientists have been chasing shadows for decades, trying to figure out what makes up this invisible stuff that outweighs regular matter 5-to-1. Enter axions, a hypothetical particle born from quantum field theory that might just hold the answer. Axions aren't your typical particles. They're ultra-light, almost ghostly, and behave more like waves than solid bits of matter. Picture ripples spreading across a pond, but instead of water, these ripples are disturbances in a hidden quantum field permeating the universe. That's the axion field, a cosmic undercurrent we can't see but might be everywhere. What makes axions so intriguing is how perfectly they fit the dark matter puzzle. They don't interact much with light or ordinary matter, which explains why we haven't spotted them yet. But their sheer numbers, trillions, could be passing through you right now, could add up to the missing mass we've been searching for. The hunt is on. Scientists are building ultra-sensitive detectors like the Axion dark matter experiment to catch these wispy particles. If they succeed, it wouldn't just solve dark matter. It would open a new window into quantum fields we never knew existed. So, could axions be the hidden architects of the universe's invisible scaffolding? The race to find out is heating up, and the answer might rewrite physics as we know it. Next up, we'll revisit an old idea that once seemed dead but might have new life: the Dirac sea. Now, let's take a step back in time to revisit an idea that once shook the foundations of physics: the Dirac sea. Back in the 1920s, physicist Paul Dirac proposed something radical. He imagined the vacuum of space not as empty nothingness, but as a churning ocean of particles with negative energy, completely filled like an infinite, invisible sea. Every possible state was occupied, leaving no room for movement, until a particle was knocked out, creating a hole that behaved like its opposite, antimatter. At the time, this wild idea helped explain the existence of antimatter like the positron, which was later discovered. But as quantum field theory evolved, the Dirac sea fell out of favor. Today, we think of the vacuum differently: a bubbling soup of virtual particles popping in and out of existence, not a static sea. Yet, here's the twist: Dirac's intuition might not be entirely wrong. Some modern theories, like those exploring the nature of dark energy or the quantum vacuum structure, echo his old vision in surprising ways. Could the Dirac sea make a comeback? Maybe not in its original form, but the idea that the vacuum is far from empty still holds. It's a reminder that even abandoned theories can leave fingerprints on future discoveries. Next, we'll dive into an even more mind-bending possibility. What if spacetime itself isn't fundamental, but emerges from something deeper? Now, let's shift gears and consider something even more radical. What if spacetime itself isn't the bedrock of reality, but something that emerges from a deeper layer of quantum fields? Think of it like temperature. You don't feel individual atoms moving in a hot cup of coffee, but their collective motion creates what we experience as heat. In the same way, spacetime might not be fundamental. It could be a side effect of tangled quantum fields interacting in ways we're just beginning to understand. This idea comes from theories like AD/CFT and holography, which suggest that the universe could work like a hologram. The three-dimensional world we see, gravity, stars, even you and me, might be a projection of information encoded on a two-dimensional surface like a cosmic barcode. It's as if the universe is running on quantum fields the way a video game runs on code, and space-time is just the graphics our brains render. But here's where it gets wild. If space-time emerges from entangled fields, then concepts like distance or even cause and effect might not be absolute. Two particles could be entangled across billions of light years, acting as if they're right next to each other in the code of the universe. This challenges everything we thought we knew about locality and could rewrite physics at its core. So, is space-time an illusion? Not exactly. It's as real as temperature is to your hand. But it might not be the deepest layer of reality. And if that's true, the next question is, what's beneath it? That's a mystery we're still unraveling. Up next, we'll tackle another cosmic puzzle. What happens to quantum fields when they fall into a black hole? Let's take a closer look at one of the most baffling puzzles in physics, the black hole information paradox, but with a twist. Instead of thinking about particles vanishing into a black hole, let's ask what happens to the quantum fields they're made of. When a star collapses or a spaceship crosses the event horizon, its matter doesn't just disappear, it's woven into the fabric of the black hole. But here's the problem: quantum fields carry information like the universe's ultimate hard drive. If that information gets erased, it violates one of quantum mechanics' core rules: information can't be destroyed. So where does it go? One wild idea is the firewall theory. Imagine the event horizon isn't just a quiet point of no return, but a raging wall of high-energy particles shredding anything that falls in. The fields encoding that information would get scrambled into pure chaos, like burning a book and saying the ashes still hold the story. But this clashes with Einstein's relativity, which says crossing the horizon should feel uneventful. No fire, no drama. Then there's the softer, stranger solution: soft hair. No, not literal hair. Think of it as faint imprints left on the black hole's surface by quantum fields as they fall in. These subtle vibrations could preserve information like grooves on a vinyl record. The fields don't vanish, they're transformed, stored in ways we can't yet decode. The stakes: if quantum fields can lose their data inside black holes, our entire understanding of reality might need an overhaul. But if the information secretly escapes, maybe through Hawking radiation or some quantum sleight of hand, then fields might be even more resilient than we thought. Either way, black holes aren't just cosmic vacuum cleaners, they're the ultimate test for quantum field theory. Next up, we'll rewind to the universe's infancy, where fields ruled supreme. Now, let's rewind the cosmic clock to a time when the universe was just a newborn fractions of a second after the Big Bang. Back then, the universe wasn't filled with stars, galaxies, or even particles as we know them. Instead, it was a seething ocean of pure energy where quantum fields called the shots. Imagine a boiling pot of water, but instead of bubbles, you've got fields vibrating at unimaginable energies, shaping the very fabric of reality. In these extreme conditions, particles as we know them didn't exist yet. The universe was so hot and dense that even the Higgs field, the one that gives particles their mass, couldn't do its job. Everything was massless, moving at the speed of light, and fields were free to interact in ways that would seem alien to us today. Then, as the universe expanded and cooled, something extraordinary happened: phase transitions, like cosmic snap freezes. Think of it like water turning to ice, but on a universe-sized scale. As temperatures dropped, symmetries in these fields broke, and suddenly, the rules of physics as we know them began to emerge. The Higgs field, for example, switched on like a cosmic light bulb, giving particles their mass and setting the stage for atoms, stars, and eventually us. But these transitions weren't always smooth. Some fields got stuck in their old configurations, creating cosmic defects, relics like cosmic strings, which are theoretical cracks in space-time thinner than an atom but stretching across the entire universe. These strings, if they exist, would be like fossilized vibrations from the early universe, carrying echoes of those first chaotic moments. And here's the wild part. Some theories suggest these strings could still be out there, warping space-time or even creating bizarre gravitational waves. It's a reminder that the universe we see today, with its orderly galaxies and particles, is just the cooled-down, settled version of a far more dramatic and fiery beginning. Next, we'll explore what happens when quantum fields get pushed to their limits near the speed of light. Now, let's shift gears to something that sounds like science fiction but is very much real: the Unruh effect. Picture this: you're floating in empty space, completely motionless. To you, the quantum fields around you seem quiet, almost empty. But if you suddenly hit the gas and accelerate, something bizarre happens. The once calm field now feels like a warm bath of particles, as if the universe itself is heating up around you. This is the Unruh effect in action, a mind-bending prediction of quantum field theory. An accelerating observer doesn't just see empty space, they detect particles where none existed before. It's not an illusion, those particles are real to them, just as real as the heat you feel from a fire. But here's the kicker: someone floating nearby, not accelerating, sees nothing. The same patch of space, two completely different realities. What makes this even stranger is its connection to black holes. Just like acceleration creates particles, so does gravity near an event horizon. This is Hawking radiation. In both cases, it's the extreme conditions, acceleration or intense gravity, that tease particles out of what seems like nothing. It's as if the universe has a hidden rule: push a quantum field hard enough and it'll reward you with particles. This effect forces us to rethink what particles even are. They're not just tiny billiard balls bouncing around, they're excitations in a field, and whether they exist depends entirely on how you're moving. It's a reminder that reality isn't as fixed as we think. Next up, we'll dive into another quantum field quirk, one that lets us measure the invisible forces lurking in empty space. Now, let's take a closer look at something that might seem like magic but is pure quantum physics: the Casimir effect. Imagine two metal plates placed incredibly close together in a vacuum, so close that there's barely any space between them. You'd expect nothing to happen, right? But here's where quantum fields throw us a curveball. Even in empty space, quantum fields are never truly quiet. They're buzzing with tiny fluctuations, popping particles in and out of existence. But when you squeeze those plates together, something fascinating happens. Only certain wavelengths of these fluctuations can fit between them, while outside, all wavelengths are free to exist. This imbalance creates a subtle but measurable force pushing the plates together, like an invisible hand nudging them closer. This isn't just a quirky lab experiment. The Casimir effect has real-world applications, especially in nanotechnology, where controlling forces at microscopic scales is crucial. Think of tiny machines or sensors where even the slightest push matters. This effect can't be ignored. But here's where it gets even wilder. Some theorists suggest the Casimir effect might hint at extra dimensions. If space has hidden dimensions curled up too small for us to see, they could alter how quantum fields behave between the plates, changing the force in ways we could measure. It's like finding footprints of something we can't even see. So next time you hear about empty space being nothing, remember, it's a seething ocean of quantum activity, and the Casimir effect is just one way we've learned to tap into it. Up next, we'll explore how quantum fields can tie themselves into knots and why these cosmic twists might still be lurking in the universe today. Now, let's unravel another cosmic mystery: knots in the fabric of quantum fields themselves. Picture a tangled thread in a sweater, but instead of yarn, it's the very fields that make up reality. These twists, known as topological defects, are like cosmic scars left over from the universe's earliest moments, when quantum fields cooled and settled into their current state. Think of it like ice forming on a pond. As water freezes, cracks and imperfections can appear. Some regions freeze one way, others another, creating boundaries between them. In the same way, as the universe expanded and cooled, quantum fields might have frozen unevenly, leaving behind defects like monopoles, cosmic strings, or textures. A magnetic monopole, for instance, would be a particle with just a north or south pole, something we've never seen in nature, but which grand unified theories predict should exist. So why haven't we spotted these cosmic knots? One possibility is they're incredibly rare. If monopoles were produced in the early universe, inflation, the rapid expansion of space, might have diluted them to the point where there's maybe just one in our entire observable universe. Or perhaps they're hiding in plain sight, masquerading as dark matter or other exotic particles. But here's the thrilling part: if we ever found one, it would be a smoking gun for physics beyond the standard model. These defects could be fossils from when electromagnetism and the nuclear forces were one unified force, a window into the universe's most extreme energies. Up next, we'll dive into a theory that bridges quantum fields and the mind itself. Could the vibrations of these fields hold the key to consciousness? Now, let's venture into one of the most controversial intersections of science and philosophy, where quantum fields might brush against the very fabric of consciousness. At first glance, the idea that tiny vibrations in quantum fields could play a role in human awareness sounds like science fiction. But some researchers, like physicist Roger Penrose and anesthesiologist Stuart Hameroff, propose just that with their orchestrated objective reduction theory, or ORCH for short. Here's the wild idea. Inside your brain's neurons, there are tiny structures called microtubules, protein filaments that help maintain cell shape. ORCH suggests these microtubules could host quantum vibrations in their molecular structure, and when these vibrations collapse, they might generate moments of conscious experience. In other words, your thoughts could be rooted in quantum field interactions at an unimaginably small scale. But before we get carried away, let's separate the tantalizing speculation from hard science. Mainstream neuroscience largely dismisses ORCH, arguing the brain is too warm and noisy for delicate quantum effects to persist. Decoherence, the tendency of quantum systems to get scrambled by their environment, would likely destroy any quantum coherence in microtubules almost instantly. Yet, defenders of the theory counter that biological systems might have evolved ways to protect quantum states, much like photosynthesis exploits quantum effects in plants. The debate raises a deeper question. Even if quantum fields aren't directly driving consciousness, could they still play a subtle role in how information is processed in the brain? Some experiments hint at quantum effects in biological systems, but none have definitively linked them to awareness. Until we have concrete evidence, ORCH remains a fascinating but unproven frontier, one that challenges us to ask whether the universe's most fundamental fields might somehow echo in the mystery of our own minds. Next up, we'll explore an even bolder idea. What if quantum fields aren't just part of reality, but the very substrate of a cosmic computation? Now, let's take a step into a mind-bending idea. What if the universe itself is running a kind of cosmic computation, with quantum fields acting like a vast neural network? Picture this: just as artificial neural networks process information by passing signals between interconnected nodes, quantum fields might be doing something eerily similar on a universal scale. Every interaction between particles, every ripple in a field, could be part of a grand, self-organizing computation that shapes reality itself. This isn't just wild speculation. Physicist and computer scientist Stephen Wolfram has been exploring this very idea through his physics project, which suggests that the universe's fundamental rules might emerge from simple computational processes. Think of it like this: if you zoom in far enough, the fabric of reality might not be made of particles or waves, but of tiny, interconnected computations happening within quantum fields. The way these fields interact, evolve, and entangle could be the universe's way of calculating its own existence. But how far can we take this analogy? Neural networks learn and adapt by adjusting connections. Could quantum fields learn too? Some theories propose that the constants of nature, like the speed of light or the strength of gravity, might not be fixed but could emerge from a kind of cosmic optimization process. It's a stretch, but it raises a fascinating question. If the universe is computing itself, what's the program, and who or what wrote the code? Of course, this is still speculative territory. Mainstream physics hasn't embraced the idea that the universe is literally a neural network, but the parallels are striking enough to make scientists pause. Whether it's Wolfram's computational universe or other theories, one thing's clear: quantum fields might be doing far more than just filling empty space. They could be the hidden circuitry of reality itself. Up next, we'll dive into an even more radical question. What if time, as we experience it, is just an illusion emerging from these deeper quantum fields? Now, let's shift gears to something even more mind-bending. What if time, the very fabric of our daily experience, isn't real at all? That's the radical question posed by the Wheeler-DeWitt equation, one of the most controversial ideas in quantum gravity. This equation, dreamed up by physicists John Wheeler and Bryce DeWitt, suggests something astonishing. When you combine quantum mechanics with general relativity, time simply disappears from the math. Poof, gone. Here's the wild part. The Wheeler-DeWitt equation describes the entire universe as a frozen, unchanging block. No past, no future, just a single, static snapshot where all possible states of quantum fields exist at once. It's like hitting pause on a movie, except the movie is reality itself. So why do we experience time flowing? Some theorists argue that time isn't fundamental but emerges from deeper quantum fields, like a hologram projected from a hidden layer of physics. Think of it this way: imagine a river. From a distance, it looks like a smooth, flowing current, but zoom in, and you'll see it's made of countless water molecules bumping and jostling in chaotic motion. Time might be like that river, an illusion created by the underlying dance of quantum fields. The equations suggest that what we call time could just be a side effect of how these fields interact, not something built into the universe's blueprint. But if time isn't real, why does it feel so undeniable? That's the paradox. Some physicists argue that our perception of time comes from entanglement, the way quantum fields link up across space, creating a kind of cosmic clock. Others think it's tied to entropy, the universe's tendency toward disorder. Either way, the Wheeler-DeWitt equation forces us to ask, is time just a trick of the mind, or is there something deeper at work? This idea isn't just philosophy, it has real consequences. If time isn't fundamental, then our entire understanding of cause and effect, of history and destiny, might need a rewrite. It's a humbling thought. The ticking clock that rules our lives could be nothing more than a shadow cast by quantum fields. Up next, we'll explore another geometric twist in the quantum puzzle, the amplituhedron, a shape that might hold the secret to how particles interact. Could spacetime itself be a projection of something even stranger? Stay tuned. Now, let's take a detour into the world of geometry, but not the kind you learned in school. Meet the amplituhedron, a bizarre, multidimensional shape that's rewriting how we think about particle interactions. Forget Feynman diagrams with their messy loops and lines. This geometric object simplifies calculations so much that it feels like cheating. But here's the kicker: the amplituhedron doesn't just make math easier. It hints that space-time and quantum fields might be illusions, projections of something far more abstract. Picture this: every collision in a particle accelerator, every photon bouncing off your skin, could be described by the volume of this shape. No space-time, no fields, just pure geometry. The amplituhedron's edges and facets encode probabilities so perfectly that physicists started wondering, are the fields we've been studying just shadows on the wall of a deeper mathematical cave? What's wild is that the amplituhedron treats spacetime as optional. In standard physics, particles interact across distances, but this shape doesn't care about where or when. It suggests that locality, the idea that things only affect their neighbors, might be a side effect, not a law. Imagine watching a movie and realizing the screen isn't the real story. The amplituhedron is like the hidden code behind the pixels. So where do quantum fields fit in? If the amplituhedron is right, fields like the Higgs or electromagnetic might be approximations, like ripples on the surface of a pond. The real action could be happening in a realm of pure math where geometry dictates everything. It's as if we've been studying smoke signals, mistaking them for the fire. This isn't just a pretty idea, it's a potential revolution. If spacetime and fields emerge from shapes like the amplituhedron, we might need a whole new dictionary for the universe. Are we closer to cracking reality's deepest secrets, or just trading one mystery for another? Up next, we'll venture where even light can't escape inside a black hole. How do quantum fields behave when gravity turns vicious? The answers might be stranger than fiction. Now, let's step into one of the most extreme environments the universe has to offer: the heart of a black hole. Here, gravity isn't just strong, it's ruthless, warping space and time to the point where even quantum fields, the backbone of reality, face their ultimate test. What happens to these fields when they cross the event horizon, that point of no return? One possibility is chaos. As particles and their associated fields plunge toward the singularity, the crushing gravity might stretch and twist them beyond recognition. Imagine a river hitting a waterfall. The smooth flow breaks into violent turbulence. Some theories suggest these fields could pile up near the singularity, creating a storm of energy and information so dense that our current physics just gives up. But there's another, wilder idea: fuzzballs. In this scenario, quantum gravity steps in before fields reach the singularity, transforming the black hole's core into a tangled, fuzzy sphere of strings or other quantum structures. Instead of a point of infinite density, you'd have a dense, vibrating mess where fields blend into something entirely new. It's like swapping a black hole's sharp, destructive center for a ball of quantum yarn. Still bizarre, but maybe less apocalyptic. The real puzzle is what this means for information. Quantum fields carry data like the properties of particles that fell in. If fields pile up or turn fuzzy, does that information get destroyed, scrambled, or preserved? The answer could reshape our understanding of reality itself. So, do black holes shred quantum fields, or does quantum gravity rewrite the rules? Either way, the interior of a black hole might be the ultimate lab for testing the limits of field theory, if only we could peek inside. Coming up, we'll revisit an old idea with a quantum twist. Could the universe's fields be a modern-day version of the ether? The answer might surprise you. Now, let's take a step back in time, way back to an idea that once ruled physics but was eventually tossed aside: the ether. This invisible substance was thought to fill the universe, a medium through which light waves traveled, much like sound needs air. But Einstein's relativity shattered that idea, proving light doesn't need a medium. So why are we talking about it now? Because quantum fields might be giving the ether a second act. Think of the Higgs field. It's everywhere, invisible, and it interacts with particles to give them mass. Sound familiar? Some physicists argue the Higgs field could be a modern-day ether, not as a medium for light, but as a cosmic backdrop that shapes reality. The difference: the old ether was supposed to be a static, absolute reference frame, which relativity killed off. The Higgs field, though, is a dynamic quantum field that doesn't break Einstein's rules. It's more like a fluid that particles swim through, slowing some down, giving them mass, while others zip through untouched. But here's where things get tricky. Calling the Higgs field an ether might be more poetic than accurate. The original ether was a failed hypothesis, while the Higgs field is a well-tested part of quantum field theory. The analogy can mislead if it suggests a return to pre-Einstein thinking. Yet, the comparison isn't totally useless. It reminds us that space isn't just empty, it's buzzing with fields that dictate how particles behave. So, is the Higgs field the ether reborn? Not exactly. But it does show how old ideas can resurface in new forms refined by deeper science. Next up, we'll tackle an even bigger question. If we're living in a simulation, could quantum fields be the code running the universe? The answer might blur the line between physics and philosophy. Now, let's shift gears to a theory that sounds like science fiction, but has some serious scientific backing. What if our universe is just an incredibly advanced simulation? And if that's the case, could quantum fields be the underlying code that makes it all work? Think about how video games create realistic worlds. They use algorithms to simulate physics, light, and even the behavior of objects. Now, imagine that on a cosmic scale. Quantum fields, with their precise mathematical rules, could be the programming framework of our reality. Every particle interaction, every force, every flicker of energy might just be lines of code executing in a higher dimensional computer. This idea isn't just wild speculation. Lattice quantum field theory, a method used to simulate quantum systems on computers, shows how complex field behaviors can be approximated using discrete grids. If we can do that in a lab, why couldn't an advanced civilization run the universe the same way? Some physicists argue that if we're in a simulation, there might even be detectable glitches, tiny errors or inconsistencies in the laws of physics, like rounding errors in a massive calculation. But here's the catch: proving this is nearly impossible. Any glitches we find could just be new physics, not proof of a simulation. And if the simulation is flawless, we'd never know the difference. Still, the idea forces us to ask deeper questions. Are quantum fields the ultimate reality, or just the user interface of something even more fundamental? Whether you buy into the simulation argument or not, it's a fascinating lens to examine quantum fields through. Next, we'll dive into one of the biggest puzzles in physics, the hierarchy problem, and why the Higgs field's energy is so bafflingly small compared to what quantum gravity predicts. Now, let's tackle one of the most puzzling gaps in physics, the hierarchy problem. Why is the Higgs field's energy so incredibly tiny compared to the colossal scale predicted by quantum gravity? It's like finding a feather floating in a hurricane and wondering how it stays so light. The Higgs field gives particles their mass, but here's the weird part. Its energy should be enormous, pulled up to the scale of quantum gravity by virtual particles constantly popping in and out of existence. Yet it's shockingly small, about a quadrillion times smaller than it should be. This mismatch isn't just a minor hiccup, it's a gaping hole in our understanding. One proposed fix is supersymmetry, a theory that introduces a shadowy twin for every known particle. These superpartners could cancel out the wild quantum fluctuations, keeping the Higgs field's energy low. But here's the catch: we haven't found any superpartners yet, and the Large Hadron Collider's silence is making physicists sweat. Another wild idea: extra dimensions. If gravity spreads into hidden dimensions beyond our four, it might seem weaker here, explaining why the Higgs field doesn't get dragged up to gravity's scale. It's like gravity's strength is diluted across unseen realms. Then there's the anthropic principle, a cosmic shrug that suggests maybe the Higgs field is small because if it weren't, we wouldn't exist to wonder about it. Universes with different Higgs energies might collapse or lack atoms, making ours a rare, life-friendly fluke. Each solution has its own headaches, but that's what makes the hierarchy problem so thrilling. It's a battle between elegance and evidence, pushing us to rethink reality itself. Up next, we'll explore how quantum fields behave when pushed to the extreme, near the speed of light, and the bizarre effects that unfold. Now let's shift gears and zoom into the realm of extreme speeds, where quantum fields don't just behave differently, they practically rewrite the rules. Imagine pushing these fields to the brink near the speed of light and watching the universe reveal some of its most mind-bending tricks. First up, the Schwinger effect, a phenomenon so wild it sounds like science fiction. In empty space, a strong enough electric field can literally rip particle-antiparticle pairs out of the quantum vacuum. It's like the field stretches reality until it snaps, creating matter from pure energy. This isn't just theoretical, it's been glimpsed in labs with ultra-powerful lasers. But here's the catch: the energy required is staggering, far beyond what we can currently muster. Yet, near black holes or in the early universe, where fields were unimaginably intense, this effect might have been commonplace. Then there's the question of Cherenkov radiation, usually seen as that eerie blue glow in nuclear reactors, where particles move faster than light in water. But in a vacuum, light speed is the ultimate speed limit, so this shouldn't happen, right? Well, quantum fields near light speed flirt with this limit in bizarre ways. Some theories suggest that if the vacuum itself has unusual properties, like in certain quantum materials or hypothetical ether-like fields, light might slow down just enough for particles to outpace it, creating vacuum Cherenkov radiation. It's a fringe idea, but it challenges everything we know about relativity and quantum fields. And let's not forget time dilation's role. As fields approach light speed, time for them slows down dramatically. A quantum field vibrating at near light speed would appear frozen to an outside observer, while its energy skyrockets to infinity, at least mathematically. In reality, quantum gravity or other effects might step in to prevent this singularity, but we're still guessing. What's clear is this: at these extremes, quantum fields don't just bend the rules, they shatter them. Next, we'll dive into one of the strangest thought experiments in physics, where random field fluctuations might conjure up something even weirder than particles: a self-aware brain. Now, let's take a step into one of the most bizarre thought experiments physics has ever dreamed up, where quantum fields might not just create particles but entire conscious minds. Picture this: in the vast emptiness of space, random fluctuations in quantum fields could, by sheer chance, assemble a fully functioning brain, complete with memories and self-awareness. This is the Boltzmann brain paradox, and it's as unsettling as it sounds. Here's how it works. Quantum fields are never perfectly still, they're always buzzing with tiny, random fluctuations. Most of the time, these fluctuations cancel each other out, but given enough time, statistically, they could line up in just the right way to form something far more complex than a particle. A self-aware brain floating in the void, convinced it's living in a real universe. The scary part: if the universe lasts long enough, Boltzmann brains might become more likely than actual evolved beings like us. This ties directly into entropy, the universe's tendency toward disorder. Over unimaginable stretches of time, entropy drives systems toward equilibrium, but it also allows for rare, temporary drops in disorder. A Boltzmann brain is one such drop, a freak accident of order in a sea of chaos. But here's the twist: if these brains are more probable than ordinary observers, why don't we experience the universe as a disjointed, fleeting hallucination? The answer might lie in the arrow of time. Our perception of time's flow from past to future could be what grounds us in a stable reality, while Boltzmann brains would exist in brief, disconnected moments. Some physicists argue this paradox is a sign we're missing something fundamental about quantum fields or cosmology. Maybe the universe isn't as old or as infinite as we think, or perhaps consciousness can't emerge from random field fluctuations at all. Either way, the Boltzmann brain forces us to confront the deepest questions about reality, observation, and the nature of existence itself. Next, we'll explore another radical idea where hidden quantum fields might be guiding particles in ways that challenge everything we know about quantum mechanics. Now, let's shift gears to a theory that turns quantum mechanics on its head. What if particles aren't just probabilistic waves, but have hidden guides steering their paths? This is the idea behind Bohmian mechanics, where an invisible quantum field called the pilot wave directs particles like an unseen hand. Here's the core of it. In mainstream quantum field theory, particles don't have definite positions until they're measured. They exist as probability clouds. But Bohmian mechanics says no, particles always have real positions, and their movements are choreographed by this hidden pilot wave field. Think of it like a boat floating on a river. The boat is the particle, and the river's current is the pilot wave pushing it along a specific path. The big difference. Bohmian mechanics brings back determinism, the idea that if you knew the exact state of the pilot wave and the particle, you could predict its future perfectly. That's a stark contrast to the randomness of standard quantum theory, where outcomes are fundamentally uncertain. Supporters argue this solves the measurement problem. No more collapsing wave functions or observer-dependent realities. But there's a catch. The pilot wave theory requires all particles to be connected instantaneously, no matter how far apart they are. That sounds a lot like spooky action at a distance, something Einstein famously disliked. And while it matches quantum mechanics predictions, it adds layers of complexity without offering new testable results, at least not yet. Critics also point out that the pilot wave field itself is undetectable, making it more of a philosophical fix than a scientific breakthrough. Still, it's a fascinating alternative that forces us to ask, is quantum randomness truly fundamental, or is there a deeper, hidden order beneath it all? Up next, we'll dive into an even stranger question. Could quantum fields be at work inside living organisms, shaping biology itself? Now, let's step into a realm where quantum fields might be shaping life itself. Could the bizarre rules of the quantum world be at play inside living organisms? This isn't science fiction. Some scientists believe biological systems, from plants to birds, might harness quantum field effects in ways we're only beginning to understand. Take photosynthesis, for example. Plants convert sunlight into energy with staggering efficiency, nearly 100% in some cases. Classical physics struggles to explain this, but quantum field theory might hold the key. Research suggests that energy in photosynthetic molecules doesn't just hop randomly. It explores multiple paths at once, like a wave, thanks to quantum coherence. This could let plants sample the most efficient route for energy transfer, almost as if they're tapping into the quantum field's probabilistic nature. Then there's magnetoception, how birds navigate using Earth's magnetic field. One theory proposes that cryptochrome proteins in their eyes host entangled electron pairs, sensitive to magnetic fields through quantum field interactions. When light hits these proteins, it might trigger a quantum state that acts like a compass needle, guiding migrations across continents. But here's the catch. While these ideas are thrilling, they're also hotly debated. Quantum effects are fragile, easily destroyed by the warm, messy environment of living cells. Critics argue that any quantum coherence in biology would vanish faster than a thought, drowned out by molecular noise. Supporters counter that evolution could have found ways to protect these quantum tricks, just as it optimized other biological processes. The truth, some evidence is compelling, like lab studies showing quantum vibrations in photosynthesis, but much remains speculative. The key is separating solid science from overhyped claims. Quantum biology is a young field, and while it's tempting to imagine cells as quantum computers, we need more proof. So are life's secrets written in quantum fields? Maybe, but for now, it's a tantalizing frontier where physics and biology collide. Next up, we'll explore a chilling what if. What if the universe's quantum fields froze solid, locking reality into place? Now, let's venture into a thought experiment that bends the very fabric of reality. What if the universe's quantum field suddenly froze solid? Picture this: every field, from the Higgs to the electromagnetic, cooling into a rigid, unchanging state, like a cosmic pause button pressed on all of existence. Particles once buzzing with motion would lock into place as if trapped in an infinite quantum ice. At first glance, this might sound like a sci-fi apocalypse, but it's a legitimate theoretical possibility. In our universe, quantum fields are dynamic, vibrating with energy that gives rise to particles and forces. But if these fields lost their energy, say, by cooling to absolute zero, they could settle into a static, lowest energy state. No more fluctuations, no more particle creation or annihilation, just a frozen snapshot of reality. What would physics look like in such a world? For starters, time itself might lose meaning. Motion requires change, and change relies on fields evolving. If fields are frozen, so is time. No ticking clocks, no orbiting planets, no chemical reactions. Even light would stop in its tracks, as photons rely on oscillating electromagnetic fields to propagate. The universe would become a silent, motionless sculpture, a stark contrast to the vibrant cosmos we know. But here's the twist: this scenario isn't just a wild hypothetical. Some theories of quantum gravity suggest that at extremely high energies or near singularities, fields could behave in ways that resemble freezing. And if the universe's expansion continues accelerating, dark energy might one day dominate so completely that it effectively cools the quantum fields into stagnation. Of course, this raises eerie questions. Could life or even consciousness exist in a frozen universe? Probably not as we know it. Life depends on entropy, chemical reactions, and the arrow of time, all of which would vanish in a static field landscape. It's a chilling reminder of how delicate the balance of our universe's active quantum fields really is. So, while the frozen field scenario remains speculative, it forces us to appreciate the dynamic, ever-changing nature of reality, and how quantum fields aren't just background actors but the very stage on which existence plays out. Up next, we'll tackle another cosmic puzzle. Why do we have so many fundamental fields in the first place? The answer might lie in a particle desert or something even stranger. Now, let's turn our attention to a puzzle that's been nagging physicists for decades. Why does our universe have so many fundamental quantum fields? Think about it. We've got fields for electrons, quarks, photons, gluons, and more, each with their own rules and interactions. It's like a cosmic zoo packed with wildly different species, and nobody's quite sure why nature needed such a crowded menagerie. This is what scientists call the field zoo problem. On one hand, it's incredible that these fields give rise to everything from atoms to galaxies. But on the other, it feels messy. Why not just a handful of elegant fields instead of this sprawling collection? Some physicists dream of a grand unified theory, one master field that could explain all the others. String theory, for example, imagines tiny vibrating strings as the fundamental building blocks, with different vibrations producing what we see as separate fields. It's a beautiful idea, but so far no smoking gun evidence has turned up. Then there's the particle desert hypothesis. This suggests that beyond the particles we've already discovered, there might be a vast emptiness, a desert, with no new fundamental fields waiting to be found. If true, it would mean the field zoo we have now is pretty much the whole show. But here's the catch: even if no new fields exist, we still don't know why the ones we have are so diverse. Could there be a deeper layer beneath all these fields, something simpler we haven't uncovered yet? Or is the universe just fond of variety? For now, the field zoo remains one of quantum physics' biggest mysteries. But every unanswered question is a chance for a breakthrough, and who knows, the next big discovery might finally explain why nature chose this particular lineup. Up next, we'll explore how quantum fields might hold the key to another cosmic riddle, the arrow of time. Now let's unravel another cosmic mystery. Why does time only move forward? At first glance, it seems obvious you can't unbreak an egg or uncook a pizza. But when you zoom into the quantum world, the laws of physics don't actually care about time's direction. Equations work just as well whether time runs forward or backward. So why does our universe have such a stubborn arrow of time? The answer might lie in the chaotic dance of quantum fields. Picture this: every particle decay, every collision, every flicker of energy in a quantum field leaves a tiny mark, a little increase in disorder or entropy. Over billions of years, these tiny changes add up, pushing the universe toward more chaos. That's why we remember the past but not the future, because entropy was lower back then, creating a clear direction for time to flow. But here's where it gets wild. Some physicists think quantum fields themselves might be the engine behind this one-way street. Take CPT symmetry, a fancy way of saying the universe should look the same if you flip time, mirror space, and swap particles with antiparticles. In theory, everything balances out, but in reality, we see more matter than antimatter, and time only marches forward. Could quantum fields be breaking this symmetry, subtly favoring one direction over the other? Or maybe it's something deeper, like fields reshuffling themselves in a way that locks time into its familiar flow. Then there's the mind-bending idea that time's arrow isn't fundamental at all. What if it's just an illusion emerging from the way quantum fields interact on a grand scale? Think of it like temperature. Individual atoms don't have a temperature, but when you zoom out, the collective motion creates heat. Similarly, time's direction might be a side effect of fields evolving in a universe that started in a highly ordered state. For now, the arrow of time remains one of physics' great puzzles. But every clue, from particle decays to the echoes of the Big Bang, hints that quantum fields are holding the secret. And if we crack it, we might finally understand why the past is set in stone while the future stays wide open. Next up, we'll dive into an even more dramatic idea. What if a rogue quantum field could tear the universe itself apart? Now, let's turn to one of the most dramatic endings the universe could face: the Big Rip. Imagine a force so powerful it doesn't just expand the cosmos but shreds it to pieces, atom by atom. This nightmare scenario hinges on a strange kind of quantum field known as phantom dark energy. Unlike ordinary dark energy, which gently pushes the universe apart, phantom dark energy has negative kinetic energy, meaning it grows stronger over time. And if it exists, it could eventually overpower every force holding reality together. Here's how it works. Right now, the bonds between particles, like the glue holding atomic nuclei or the electromagnetic fields keeping electrons in orbit, are stronger than dark energy's pull. But if phantom dark energy keeps intensifying, there could come a moment when it outmuscles even these fundamental forces. First, galaxies would be ripped apart, then stars, then planets. In the final moments, atoms themselves would unravel as their binding fields are overwhelmed. Even space-time might fracture, leaving the universe a cold, empty void with no structure left at all. The terrifying part: some models suggest this could happen in as little as 20 billion years, a blink of an eye on cosmic scales. And while it sounds like science fiction, phantom dark energy isn't ruled out by current observations. In fact, certain measurements of the universe's expansion hint that dark energy's strength might not be constant. It could be increasing, inching us closer to this catastrophic fate. But here's the twist: not all physicists buy the Big Rip. Some argue that quantum fields can't sustain negative kinetic energy without violating deeper physical laws. Others propose that unknown effects like quantum gravity or hidden dimensions might stabilize dark energy before it goes rogue. The debate is wide open, and that's what makes this theory so gripping. Whether the Big Rip is our destiny or just a cosmic scare story, it forces us to confront how delicately balanced the universe's quantum fields really are. Up next, we'll explore an even wilder idea, a theory where quantum fields don't just end the universe but somehow resurrect everything at the very edge of time. Now, let's take a sharp turn from cosmic destruction to something even more mind-bending: resurrection. Not in a spiritual sense, but through the sheer power of quantum fields. This is the omega point theory, proposed by physicist Frank Tipler, and it's one of the most audacious ideas in modern cosmology. Tipler's theory suggests that as the universe approaches its final moments, whether through a big crunch, heat death, or even the big rip we just discussed, quantum fields could evolve in a way that effectively brings back every consciousness that ever existed. Yes, you heard that right. Every thought, every experience, every person could be reconstructed by the universe itself, not as a spiritual afterlife but as a physical inevitability. Here's how it supposedly works. As the universe collapses or reaches maximum entropy, the computational capacity of quantum fields would become infinite. Tipler argues that this would allow the universe to simulate every possible state it's ever been in, effectively recreating all past moments, including every conscious being that ever lived. It's like the universe becomes a cosmic computer running the ultimate replay, but with you and me and everyone else genuinely experiencing it again. But let's pause for a reality check. While the idea is thrilling, most physicists dismiss the omega point as speculative at best. For one, it relies on assumptions about quantum fields that aren't supported by current physics, like infinite energy densities or perfect computational efficiency. There's also no known mechanism for how consciousness could be stored in fields or reconstructed from scratch. Critics argue that Tipler's theory leans more into philosophy than hard science, blending physics with near-mystical claims. That said, the omega point raises fascinating questions. Could quantum fields, in some extreme future state, really encode the entirety of reality's history? And if so, what does that say about the nature of time and existence? Even if the theory isn't widely accepted, it pushes us to think about the universe in ways that stretch far beyond textbooks. So, whether you see the omega point as a profound truth or a sci-fi fantasy, it undeniably adds a wild twist to our understanding of quantum fields. And with that, we've reached the end of our journey through 30 mind-bending theories. From zero-point energy to cosmic resurrection, one thing's clear: quantum fields aren't just the invisible scaffolding of reality. They might be the key to its greatest mysteries. Which theory blew your mind the most? Drop your thoughts in the comments below, and don't forget to like and subscribe for more deep dives into the universe's biggest puzzles. Until next time, keep questioning everything. And just like that, we've journeyed through 30 astonishing theories that reveal how quantum fields might shape or even shatter our understanding of reality. From the eerie possibility of vacuum decay wiping out the universe in an instant, to the mind-bending idea that spacetime itself could emerge from entangled quantum fields, these concepts don't just challenge textbooks, they rewrite them. Think about it, quantum fields aren't just passive backdrops to the cosmos. They're dynamic, unpredictable, and possibly the most fundamental layer of existence. They give particles mass, stitch together the fabric of spacetime, and might even hold the secrets to dark matter and cosmic resurrection. Whether it's the Higgs field's hidden mechanics or the spine-tingling notion of a universe-wide quantum simulation, each theory peels back another layer of the cosmic onion. So here's the big takeaway. Reality as we know it might be far stranger, far more malleable than we ever imagined. And while some of these ideas push the boundaries of current science, they all share one thrilling thread: quantum fields are the universe's ultimate architects, and we're only beginning to decode their blueprints. Now, over to you. Which of these theories left you staring at the ceiling at 3 in the morning? Was it the cosmic horror of vacuum decay, the elegance of emergent spacetime, or the wild optimism of the omega point? Drop your favorite in the comments. I'd love to hear which one hooked you. And if you enjoyed this deep dive into the quantum unknown, Don't forget to hit that like button, subscribe, and ring the notification bell so you never miss our next exploration of the universe's biggest mysteries. Until next time, keep looking up and questioning everything.